Welcome to the Deep Dive. We're the show that cuts through the noise to get you the insights you actually need. Today, we're plunging into something almost every software architect grapples with. How do you build systems that can last, that can evolve, when technology itself is just constantly shifting under your feet?
Yeah, it often feels like you're trying to build a castle on shifting sand, right?
Exactly. And this idea of finding a simple best practice, it feels, well, pretty mythical most of the time. But, okay. We're not just here to describe the quicksand. Our mission today is to give you a framework, something powerful to help navigate this complexity. We're diving deep into a really fascinating book, Software Architecture, The Hard Parts, Modern Trade-off Analyses for Distributed Architectures. It's by Neal Ford, Mark Richards, Pramod Satellage, and Zhamak Dehghani. And it promises to help us and help you make better architectural decisions by embracing what they call modern trade-off analysis.
And that phrase, the hard parts, it's really key. They're not just talking about things that are, technically difficult to code.
Yeah.
They mean those foundational structural pieces of software. The things that, once they're in place, are incredibly hard, sometimes almost impossibly hard to change later on.
Like a building's foundation.
Exactly like that. Once it's poured, changing it involves complex, often really messy trade-offs. So this deep dive, it's about understanding why these problems are so tough, especially in today's distributed architectures.
Okay, so with that foundation laid, what are the absolute must-know patterns and concepts we're really getting into today?
Well, we're going to cover a lot of ground.
Yeah.
From really understanding coupling, which is fundamental, to practical strategies for breaking apart those big, stubborn, monolithic systems. And even looking at how to manage data in these new distributed ways. Think of it as a roadmap for those really tricky architectural dilemmas you face.
Okay, let's unpack that core challenge then. The book is very clear. This whole idea of a best practice in software architecture, it's often a myth.
It really is.
Instead, it's about balancing forces, finding the least worst design, maybe. Why is that best practice idea so misleading now?
Well, it's largely down to the sheer speed of change in the software world.
Yep.
What seemed best even 5, 10 years ago. It might be completely obsolete now. Think about it. Just a decade ago, maybe a bit more. Orchestration-driven SOA, service-oriented architecture, that was the dominant style for big companies.
I can remember that.
And now, you almost never hear about it for new projects. The shift, especially towards microservices, it happened because of external things like open source and Linux becoming truly viable options.
Right, and the tools.
And then the automation tools, Puppet, Chef, Kubernetes they made, managing those operating systems, essentially free, operationally speaking. This constant flux just makes any kind of timeless advice about specific technologies, well, pretty much impossible.
Which is exactly why the book shifts the focus, isn't it? It's less about how you implement something with technology X or Y, and more about why one choice gives you better trade-offs than another in this specific situation. It's about principled decisions when things are new, not just following a recipe.
Exactly. It's about thinking frameworks, not just blueprints.
So how do we start making those principled decisions? Where do we begin?
It starts with the building blocks.
Okay.
And a really core concept here is coupling. The book gives a simple definition.
Yeah.
Two parts of a software system are coupled if a change in one might cause a change in the other.
Sounds straightforward enough. So what's the catch? What do architects often miss?
Well, the insidious part, the tricky part, is that coupling isn't always obvious. You might think two services are totally independent, but maybe there's a shared database table or some unspoken assumption about how data flows between them, and that creates these invisible sort of death grips that can totally derail you later.
Ah, okay.
That's why the authors lay out this really useful 3-step framework for modern trade-off analysis. Step 1, find out what parts of your system are actually tangled up together.
Find the entanglement.
Right. Step 2, analyze how they're coupled. What's the nature of that connection?
Okay.
And step 3, assess the trade-offs. What's the real impact if you need to change one of those coupled parts? Sounds simple, but like always, the devil's in the details.
And central to really using that framework is this concept they call the architecture quantum. Can you break that down for us?
Sure. So the architecture quantum, they define it as an independently deployable artifact with high functional cohesion, high static coupling, and synchronous dynamic coupling.
Okay, that's a mouthful. Let's unpack that definition.
Yeah, let's do that. First, independently deployable. This means each quantum can be pushed out, deployed as a separate unit.
So monolith is just one big quantum.
Exactly. A traditional monolithic app is, by definition, a single architecture quantum.
Mhm.
But in distributed systems, like microservices, the goal is usually to have multiple quanta that lets you deploy and scale different parts independently.
Got it. What about high functional cohesion?
That just means the quantum does one thing well. It models a single business domain or a specific workflow. It keeps the scope tight.
Okay. Then there's static coupling.
Right. Static coupling is about how things are wired together at build time or deployment time. Think dependencies on operating systems, frameworks, shared libraries.
Hmm.
And here's where it gets really interesting and often painful. A shared database between services that often prevents them from forming separate architecture quanta,
Ah, even if they look like separate services.
even if they're deployed separately. That shared data schema forces them to act like one big, tightly coupled unit from a change perspective.
Okay, that makes sense. And the last part, synchronous dynamic coupling.
Right, dynamic coupling. This is all about how quanta communicate at runtime. Are they making synchronous calls to each other, waiting for a response? Or is it asynchronous, like firing off messages?
And that choice has big consequences.
Huge consequences. It directly impacts critical abilities, performance, scalability, elasticity, reliability. Think about elasticity, for example.
Right, handling sudden bursts.
Yeah, like that concert ticket site going from 20 users to 3,000 in seconds. If your services are all making synchronous calls to each other, waiting around, that elasticity is going to suffer badly.
So bringing this together, why is understanding these specific terms, static versus dynamic coupling, the quantum, so important for you listening?
Because it gives you a language, a framework, to objectively measure and assess the real hardness
Sure.
of your architectural choices. You can start to predict the downstream impacts. It moves you away from just gut feelings toward a more scientific, analytical approach to architecture.
Okay, so we understand the building blocks, the quanta, the coupling. Now let's talk about the why. Why break things apart in the first place? This leads us to architectural modularity.
Exactly.
And the key insight you mentioned is that decomposition isn't always about going full microservices, right? You might end up with a more modular monolith or maybe a microkernel architecture. Those can still offer big benefits.
Absolutely. It's about choosing the right level of modularity for your needs.
So what are the main things driving us towards more modularity?
The book details several key drivers. First up is maintainability. Just the basic ease of adding, changing, or removing features.
Yeah, that sounds crucial.
Think about adding a simple field, like an expiration date for a wish list item, in a classic monolithic layered app. That change often ripples across all the layers: UI, business logic, data access. It might involve multiple teams.
Painful.
Very. Compare that to a well-designed service-based or microservices architecture. The change scope is much smaller, often contained within a single service, much easier to manage.
Right, makes sense. And then there's deployability. You said it's not just about ease, but frequency and risk.
Exactly. Frequency and risk. There's that great quote from Matt Stein. If your microservices must be deployed as a complete set in a specific order, please put them back in a monolith and save yourself some pain.
Huh. Yeah, that's a good one.
Because monoliths, by their nature, bundle lots of changes together. This increases the risk of each deployment and often forces teams into these slow, infrequent release cycles, maybe monthly, where you push out a whole bunch of changes that haven't really been tested together in production.
Okay. Then we have scalability and elasticity. How do they differ again, and how does modularity help here?
So scalability is about handling, let's say, predictable, gradual growth, more users over time. Elasticity is for those sudden, unpredictable spikes, that concert ticket example again.
Got it.
Modularity helps both, especially with smaller, finer-grained services. If they have a really small mean time to start up MTTS, you can spin up new instances incredibly quickly to handle load.
But there's a catch.
There's often a catch. Synchronous communication between those services can really put a damper on both scalability and elasticity because of the waiting involved.
Right. And the last driver.
Availability and fault tolerance. Basically, can the system stay responsive even if parts of it fail? Monolithic systems inherently struggle here. If one critical component goes down,
The whole thing goes down.
often, yes. A single point of failure can take out the entire application. Modularity helps isolate failures.
Okay, to make all this concrete, let's introduce our running example for this deep dive. The CSOPS Squad Saga.
Ah, yes. The saga begins.
It's a monolithic problem ticketing application, and it's in deep trouble. Frequent freezes, reliability issues, changes take forever, all stemming from this fundamental lack of modularity. We'll keep coming back to this as we explore solutions.
Sounds like a classic case.
Definitely. So we know why we might want to break things apart. Now, how do we actually do it without making things worse?
Right. And the book gives a really important warning up front.
Mm.
Avoid the elephant migration anti-pattern.
Elephant migration.
Yeah, the idea of just blindly breaking things apart one bite at a time. It sounds sensible, but it often leads to what people call a big ball of distributed mud, or even worse, a distributed monolith, where everything is technically separate, but still hopelessly tangled together.
Okay, so no random hacking. What are the structured approaches?
The book highlights two main ones. First is component-based decomposition. This is more of an incremental, refactoring-driven approach. Think of it as a stepping stone, maybe towards a service-based architecture.
How does that work in practice? What's a key pattern?
Well, one pattern that's surprisingly powerful is just identify and size components. It sounds basic, but it's about finding those parts of your code base that have just sort of grown organically into these huge, unmanageable blobs.
Like finding the knots in the string first.
Exactly. It's diagnostic. You figure out which pieces are just too big or maybe too small and tangled to be good candidates for pulling out cleanly.
So you diagnose first.
You diagnose first.
Yeah.
Then you can move to patterns like create domain services, which is where the payoff is. You take those logical groups of components you identified and actually make them independently deployable units.
And the SysOps squad team used this.
Yeah, that's where they started. They analyzed their massive code base, looked at metrics, figured out which components were causing the most pain and were the most tangled. They used that to refactor things like namespaces just to get a clearer picture of the dependencies before they even started talking about building separate services.
Okay, that's the incremental way. What's the other approach?
The other one is tactical forking. This is described as, well, a more pragmatic approach for those really messy situations, the true big balls of mud. Instead of painstakingly trying to untangle incredibly complex dependencies and extract pieces, you do something pretty bold.
Yeah.
You literally clone the entire monolith.
Clone the whole thing.
Clone the whole thing, maybe multiple times. Then in each clone, you basically just delete all the code you don't need for the specific service you want that clone to become.
Wow, okay. That simplifies the initial separation.
It dramatically simplifies the initial refactoring and lets different teams work in parallel on their respective clones without tripping over each other quite so much. It's definitely a bolder move, but sometimes necessary for systems that seem completely intractable otherwise.
But how do you even know if your codebase can be decomposed effectively before you start cloning or major refactoring?
That's a great question. The book mentions using code metrics as indicators. Things like afferent and efferent coupling, basically, incoming and outgoing dependencies for a component, and also distance from the main sequence, which is a more complex metric that looks at the balance between how abstract a component is and how unstable likely to change it is. These can help you identify potential zones of pain or zones of uselessness where decomposition might be extremely difficult or just not worth the effort.
So the good news for you listening is that these aren't just random ideas. There are structured techniques, metrics, ways to approach this massive task of breaking down a monolith, like the SysOps Squad's application, without creating total chaos.
Right, gives you a more engineered approach.
Okay, let's shift gears to what is often, maybe arguably, the hardest part of moving to distributed architectures, managing the data.
Data, yes. The book really acknowledges this tension. It's often the biggest hurdle.
Why is it so incredibly difficult? What are the big drivers pushing us to break up monolithic databases?
Oh, there are several critical ones. Change control is massive. With a shared database, if you change a table schema, you have to find and redeploy every single service that touches that table, even indirectly if you forget one.
Boom.
Exactly. Things break unexpectedly. Moving to bounded contexts where each service owns its data isolates those changes.
That ties into contracts, right?
Precisely. Explicit contracts between services mean a service doesn't necessarily care if a column name changes in the owner's database, as long as the contract it consumes stays the same. It abstracts the database away.
Okay, what else?
Connection management. A shared database can get overwhelmed with connections, especially as you scale out multiple instances of different services all hitting it. You run out of connections, performance tanks, you get timeouts.
Right.
Scalability is another. A monolithic database forces all services to scale together with the database, even if only one small part of the application is actually experiencing heavy load. And of course, fault tolerance. A single monolithic database is a massive single point of failure.
Yeah, that's a big one.
And maybe most fundamentally, coming back to our earlier point,
Yeah.
a shared database physically prevents you from achieving multiple architecture quanta. It keeps everything locked together as one big coupled unit, no matter how many services you think you have.
So given all those compelling reasons, how do you actually do it? How do you pull that monolithic database apart? The book lays out a 5-step process.
Yeah, it's a structured approach. Step 1, analyze the database and create data domains. You look at your tables, views, stored procedures, triggers, foreign keys, all of it. And you start grouping things that belong together logically based on business domains. Then you visualize the dependencies between those domains. Those are the connections you need to eventually break.
So mapping it out first.
Mapping it out. Step 2, assign tables to data domains and schemas. You physically move tables into their own database schemas, one per domain, and you establish a strict rule. Services can only access data outside their own domain by calling the owning service, never by directly querying the other domain's schema.
Enforcing boundaries.
Crucial. Step 3, separate database connections to data domains. You change the connection string so each service only connects to its designated schema. It can't even see the others directly anymore.
Okay.
And then implicitly, once you've done that logical and connection separation, the path is clear to eventually switch over to independent servers if needed for scaling or fault tolerance. The logical separations is the hardest part.
This often opens the door to polyglot persistence, doesn't it? The idea that you don't have to use the same database type for everything.
Exactly. No one size fits all. You pick the right tool for the job. Maybe you need a relational database for your core transactional data where consistency is king. But perhaps a key value store is perfect for session data or caching super-fast lookups. Maybe a document database makes sense for product catalog information that changes shape frequently.
Flexible schemas.
Right. Or a graph database if you're modeling complex relationships, like a social network, or detecting fraud rings. Each has different trade-offs regarding consistency models, scalability, ease of use, query capabilities. You choose based on the specific needs of that service or data domain.
And we saw this exact debate in the SysOps Squad saga, right, with the customer survey data.
We did. Skylar on the UI team was pushing hard to move the survey data from the main relational database into a document database. Why? Because marketing kept changing the survey questions, and the flexible schema of a document store would make that much easier and faster.
But the database team wasn't thrilled.
No. Devin and Dana were worried. They raised concerns about data replication complexity, potential consistency issues, and just the general disruption to their established processes. That was a classic trade-off analysis.
How did they land?
Ultimately, the need for flexibility and responsiveness for the marketing team won out. They decided the benefits of the document database for that specific use case outweighed the initial concerns about replication, which they planned to address with specific patterns later on. It highlighted that different teams often value different characteristics.
Okay, let's zoom in on service size itself. The Goldilocks problem, not too big, not too small. The book talks about these opposing forces, granularity disintegrators pushing you to split services, and granularity integrators pushing you to keep them together. What are some key disintegrators? Reasons to make services smaller?
Well, one big one is just service scope and function. Is the service trying to do too many fundamentally unrelated things? Is it hard to even give a clear, concise name? That's often a sign it should be split.
Like the notification service example.
Exactly. Handling email, SMS, and physical postal letters. Maybe those have different of characteristics like frequency of change or scaling needs that they warrant separate services. Another disintegrator is code volatility. If one part of a service changes all the time, while another part is super stable,
Split them.
consider splitting them. Isolate the volatile part so changes there don't force you to retest and redeploy the stable part unnecessarily. Like in CSAP Squad, the postal letter generation logic changed weekly, but email SMS templates were stable. Separating them reduced deployment risk for the stable functions.
Makes sense. What about the integrators? The forces pushing back, keeping things together?
Database transactions are a major integrator. If you absolutely need a traditional AC transaction, atomic, consistent, isolated, durable across several operations, you might be forced to keep those operations within a single service boundary. Because true ACID transactions generally don't work reliably across multiple distributed services and their separate databases.
Right. Distributed transactions are tricky.
Very tricky, and often don't provide the same guarantees. Another integrator is workflow and choreography. If a single business process requires a whole lot of back and forth, synchronous communication between multiple services, that can kill performance due to network latency. It also increases coupling. Sometimes keeping closely related steps together in one service is simpler and faster.
So the secret, if there is one, is finding that balance between these push and pull forces for your specific context.
That's exactly it. It's always about balancing the trade-offs.
Can you give us another CSOP squad example of this balancing act?
Sure. Remember their decision about the ticket assignment service. They had logic for assigning a ticket to an expert and separate logic for routing it based on rules. These were clearly distinct functions,
Right.
but they were very tightly coupled. The assignment needed the routing information immediately, synchronously, so they made the trade-off to consolidate them into a single service.
What was the downside?
The downside was that a change to just the assignment algorithm would now require testing and deploying the routing logic too, increasing that change scope slightly. But the upside, better performance, simpler error handling, easier workflow control for that tight interaction, outweighed the downside in their context.
In the customer registration example?
Yeah, that one required an all-or-nothing ACID transaction, because you can't really have half a customer registered across different services if one fails.
Right.
So instead trying to force a distributed transaction pattern that wouldn't give them true ACID guarantees, they integrated those steps into a single registration service. They addressed the potential security concerns not by architectural separation, but by careful design within that service using a custom security library.
So integration won there due to the transaction needs.
Correct. The need for ACID trumped the desire for finer granularity.
Okay, so let's say we've broken our monolith apart, maybe into nicely sized services. Now the challenge flips, doesn't it? Now we have to figure out how to stitch them back together effectively so they can actually work as a coherent system.
Yes, it's a whole different set of problems, but just as complex. Where do you start? Often with code reuse patterns. How do you share logic without creating new monoliths?
Right. The book contrasts shared libraries with shared services. What's the core difference?
So a shared library is something you compile into your service. It's a build time dependency. It's versioned. The risk is primarily at compile deploy time. If you update a shared library, you might need to retest and redeploy all the services using it, but versioning helps manage that.
Okay.
A shared service is a runtime dependency. Your service makes a network call to it. This is often better if the shared logic changes very frequently, as you only deploy the shared service, but
There's always a but.
always. Shared services introduce performance hits because of the network calls. They introduce runtime risk. What if the shared service is down? And they create fault tolerance issues. If it fails, all its dependents fail too.
How did SysOps Squad handle this for their common database logic?
They had this debate. Should they create a shared ticketing data service or use a shared library? They looked at the history and realized the core ticketing database logic actually changed quite infrequently. And performance, especially for the customer-facing ticket creation part, was critical. So they opted for a shared library. The performance and fault tolerance benefits outweighed the slightly increased deployment coordination effort needed when the library did change.
What about reusing code for those non-domain operational things, logging, monitoring, security checks?
That's where patterns like the sidecar pattern, often used with a service mesh, really come into their own. A sidecar is a separate container deployed alongside your service container. The service mesh infrastructure can inject these sidecars automatically. They handle all that operational cross-cutting stuff, routing, metrics, tracing, maybe some security aspects transparently to your application code.
So it keeps the main service code cleaner?
Much cleaner. It decouples those operational concerns. It provides a consistent way to manage them across all your services, even if they're built in different languages or frameworks. The book calls this an orthogonal reuse pattern because it cuts across your domain logic.
And what's a reuse strategy we should definitely avoid, an anti-pattern?
The classic anti-pattern is creating a single, massive, centralized service for a core concept, like, say, customer service.
But doesn't that sound logical? Put all customer stuff in one place.
It sounds logical, but it creates incredible brittleness. If every single other service in your system needs to call this central customer service to do anything, any change to that customer service risks breaking everything else. It becomes a huge development bottleneck because everyone needs to coordinate with that team. And it's a massive single point of failure at runtime. Avoid the God service.
Okay, good warning. Stepping back again. Once we have these services, how do they actually coordinate to get work done? Let's talk distributed workflows. How do services communicate to complete a business process?
Right. The two main styles here are orchestration and choreography.
Let's start with orchestration.
With orchestration, you have a central coordinator, an orchestrator service. It knows the whole workflow and explicitly tells other services what to do step by step. Service A, do task 1. Okay, now Service B, do task 2 based on A's result.
What are the benefits?
The benefits are usually clearer control over the workflow logic. It's easier to see the whole process in one place, easier to track the state, and often easier to implement complex error handling and compensation logic.
And SysOps Squad used this.
They did for their main ticket processing workflow. They were really concerned of tickets getting lost or stuck in the wrong state. Having a central orchestrator made it easier to track status and handle failures reliably. The downside, though,
Bottle.
the orchestrator itself can become a performance bottleneck or a single point of failure if it's not designed very carefully.
Okay, so what's the alternative? Choreography.
Choreography is the opposite. It's decentralized. There's no central boss. Services react to events that other services publish. Service A finishes its task and publishes a task-a-done event. Services B and C are listening. Maybe Service B reacts and does its thing, publishing a task-a-done event, and so on.
Sounds more resilient, maybe.
It can be. It often leads to higher responsiveness, better scalability, because there's no central bottleneck, and the services are much more decoupled. They don't need to know about each other directly, just about the events.
But the downside?
The downside is that it can become really hard to see the overall workflow. Tracking the state of a process that spans many event-driven services can be complex. And implementing robust error handling and compensation across all those independent actors gets significantly trickier.
So the choice really depends on the specific workflow.
Absolutely. How complex is it? How important is end-to-end visibility versus maximum decoupling and responsiveness? Trade-offs again.
Building on that, let's really dive into transactional sagas. This is the pattern you use when you need something like a transaction across multiple services, but a traditional ACT transaction isn't possible.
Correct. A saga coordinates a sequence of local transactions, one within each participating service. Each service commits its own piece of work independently.
But what happens if something goes wrong halfway through?
That's where compensating actions come in. If a step in the saga fails, the saga coordinator, or the services themselves in a choreographed saga, triggers compensating actions for all the preceding steps that did succeed, effectively rolling back the business operation.
So if you registered the user but failed to set up their profile?
A compensating action would perhaps deregister the user or mark their account as incomplete.
What are the challenges with these compensations?
The biggest challenge is the lack of true isolation. Because each local transaction commits immediately, other processes might see that intermediate state before the whole saga completes or is compensated.
So you could see a registered user who doesn't actually have a profile yet.
Exactly. That data might be visible temporarily. And designing reliable compensating actions that truly undo the original step without causing other side effects can be really difficult.
How do you manage the complexity of these sagas?
The book recommends modeling them explicitly, often using saga state machines. This visually maps out all the possible states and transitions in the distributed workflow success paths, failure paths, compensation paths.
Like the SysOps Squad ticket process.
Yeah, mapping out start ticket created, payment processed, assignment requested, ticket assigned, and also showing the failure transitions and compensating actions for each step. It makes the logic clear. Some teams even use programmatic annotations or attributes in their code to define which methods are part of which saga and what their compensating actions are. This helps with understanding and also defining the scope for testing these complex interactions.
Okay, shifting focus slightly. Let's talk about the contracts between services. You call them the essential glue. What are the key trade-offs when defining how services talk to each other?
It really boils down to strict contracts versus loose contracts.
Strict first.
Strict contracts are things like gRPC with protocol buffers, or maybe JSON, where you rigorously enforce a schema using something like JSON schema. They guarantee fidelity. You know exactly what data structure you're getting, almost like a remote method call.
Sounds good. What's the downside?
The downside is tight coupling and brittleness. If the provider changes the contract even slightly, adds a field, renames something, it can break all the consumers instantly. It makes evolution harder.
Okay, so what about loose contracts?
Loose contracts are more like typical REST APIs using JSON without strict schema enforcement, or maybe GraphQL, where the consumer asks for exactly what it needs. They offer much higher decoupling and evolvability. The provider can add new field without breaking existing consumers.
But there must be a trade-off there, too.
Of course, you lose that guaranteed contract fidelity. The consumer has to be more tolerant of unexpected data or missing fields. You often need other mechanisms like fitness functions, maybe consumer-driven contracts, to ensure that providers and consumers don't drift too far apart and break inadvertently.
And you mentioned an anti-pattern here.
Yes, stamp coupling. This is when a service passes a huge data object to another service, even though the receiver only actually needs one or two fields from it.
Why is that bad?
It creates unnecessary coupling. The receiver is now coupled to the entire structure, even the parts it doesn't use. And at scale, it can be a massive waste of network bandwidth, sending all that extra data back and forth. Be specific about what data you exchange.
And the SysOp Squad example for contracts.
They made an interesting choice for their mobile application interface, because getting updates approved and rolled out through the public app stores can be slow. They decided to use loose contracts between the mobile app and the back-end services. This gave the back-end team more flexibility to evolve their APIs without immediately breaking older versions of the mobile apps still out in the wild. They traded strictness for evolvability.
Makes sense. Okay, finally, let's look ahead a bit, particularly at how we manage analytical data. The book talks about the evolution towards data mesh. What is this and why is it significant?
Right, data mesh represents a pretty fundamental shift in thinking about analytical data. To understand it, you have to see the evolution. We started with data warehouses.
Centralized, right?
Centralized, yes. Data from various operational systems was extracted, heavily transformed, the TL and ETL, and loaded into a rigid, predefined schema optimized for reporting. The problem was, these ETL processes were often brittle bottlenecks, and the domain knowledge from the source systems often got lost in the standardized schema.
Okay, then came data lakes.
Data lakes were also centralized, but the idea was to dump raw data from source systems first and figure out the schema later, schema on red. This was much better for things like machine learning that needed raw data.
But still centralized.
Still centralized, and the burden shifted. Now, the consumers of the data lake, data scientists, analysts, had to make sense of all these disparate raw data sets. It could become a data swamp, and data quality and discoverability were often big challenges. Data staleness could also be an issue with batch updates.
So how does data mesh try to solve this?
Data mesh takes a completely different approach. It's decentralized and socio-technical. It applies the same kind of domain-oriented thinking we use in microservices, but applies it to analytical data.
Decentralized analytical data.
Yes. And it's built on a few key principles. First, domain ownership of data. The business domains that create or know the most about the operational data also own the responsibility for providing that data as a trustworthy analytical data product.
So data stays closer to the source experts.
Exactly. Second, data as a product. This is crucial. Domains don't just dump data. They curate it, clean it, document it, and make it discoverable and usable, treating it like a product for internal consumers. Third, there's a self-serve data platform that provides the tools and infrastructure domain teams need to build, deploy, and monitor their data products easily.
And what's the architectural building block for this? Is there a quantum equivalent?
There is. They introduced the data product Quantum, DPQ. You can think of this as an architectural component built adjacent to and coupled with an operational service, or its architecture quantum. It's operationally separate but serves as a specific interface for providing that service's data for analytical purposes. It's like a cooperative quantum dedicated to analytics.
How does this apply to SysOp Squad?
Well, imagine they need to do sophisticated planning for their expert support staff supply. Instead of trying to pull everything into a central warehouse under data mesh, the team owning the ticket service would expose a tickets DPQ. The team owning user maintenance exposes a user DPQ. The survey team exposes a survey DPQ. Then a new team, maybe focused on workforce planning, can consume these reliable data products via the self-serve platform to build their own expert supply DPQ or analytical models.
So it decentralizes the creation and ownership of analytical data, aligning it with the business.
Precisely. It aims to scale analytical data management by empowering the domains themselves, avoiding the bottlenecks of central data teams trying to understand everyone's data.
So for you listening, the key takeaway is that this data mesh paradigm offers a potentially powerful way to handle complex analytical needs in large organizations, avoiding those pitfalls of previous centralized models by aligning data ownership and accountability directly with the business domains.
It's definitely a paradigm shift to watch.
Okay, as we start to wrap up this really deep dive, what's the single most important message you think architects should take away from the hard parts?
I think the central message, the core thesis, is that there are simply no silver bullets in software architecture. There's no single right answer.
Yeah.
The real skill, the defining characteristic of a great architect, is the ability to perform objective, nuanced trade-off analysis. It's about understanding the options, understanding the forces at play, and consciously choosing the least worst combination of compromises for your specific context.
And to help internalize that, it's worth repeating that three-step framework they provide. 1, find the entangled parts. 2, analyze how they're coupled. 3, assess the trade-offs of changing them.
Exactly. And refining that skill takes practice. The book suggests practicing qualitative analysis, really thinking through the pros and cons. Use MECE lists, mutually exclusive, collectively exhaustive when comparing options. Make sure you're covering all the angles and not comparing apples to oranges.
And
Crucially, always avoid the out-of-context trap. Don't just grab some advice you read on a blog or heard at a conference and apply it blindly. Dig into why that advice might have worked in that specific situation and analyze if those conditions apply to your unique problem. Context is everything.
So here's a final, maybe provocative thought for you to take away and chew on, directly inspired by the book's philosophy. Don't allow others or even yourself to force you into just evangelizing the latest shiny technology or pattern. Instead, always bring the discussion back to trade-offs. What are we gaining? What are we losing? Why is this the right set of compromises for us right now? Because that kind of analysis, that principled decision-making, that's where an architect provides real, lasting, sustainable value to an organization.
Well said.
Now, I want to turn it over to you. What are the architectural hard parts you're currently grappling with in your own work? What questions did this deep dive spark for your systems? We'd love for you to continue the conversation.